Hey everyone, in this video I'll be going over another set of stoichiometry problems. These are a little bit more complicated, and so we titled this video Applied Stoichiometry. They involve chemical reactions, and you'll see. Just go ahead and take a look at this video. Let's go ahead and get started, alright? Photosynthesis is a process that takes place in plants, algae, and some bacteria to produce food from carbon dioxide and water using sunlight. And we have we're provided with a chemical reaction down here. I'm just going to box it in. If 5 moles of water are used during the process, how many moles of glucose is made? So we know that the formula obviously for water is H2O, right? And we're starting off with 5 moles of H2O for that reason, because that's what they give us. And they're asking us specifically for the moles of glucose that are made. Now, since we know that we essentially are going to be converting from one substance to the next, in this case, we are converting from moles of H2O to moles of glucose, which is C6H12O6. We'll be converting from one substance to the next. We have to go through moles in order to do that, right? Because we cannot convert from like grams of H2O to grams of glucose. You always have to go from moles of one substance to moles of the next, and then from there you can go from moles of that substance to like grams. But in this case, we are starting with 5 moles of water, so that allows us to do a direct conversion from moles of water to moles of glucose. Now let's go ahead and see what this looks like. So since we're starting with 5 moles of H2O here, we are now able to do that mole to mole conversion, right? And since we'll be doing a mole to mole conversion, we're essentially going to be going from moles of H2O to moles of C6H12O6. This is a very simple problem because it's just a mole to mole conversion. Now, we know that we will be doing this mole of H2O to mole of C6H12O6 conversion. Now, in order to solve for this, look, we're given the chemical reaction up here. Now we can work with this given chemical reaction. Essentially, all that we need to do now is balance this equation and then go ahead and plug in the values. Now, when you balance this equation, you should be getting, if you don't know how to balance a reaction, go ahead and take a look at our other video, which goes over how to balance these chemical reactions. Here, I'm just going to briefly just write what their coefficients should be. So you should have 6 moles of CH2, 6 moles of H2O, and 6 moles of O2 when you go ahead and balance this reaction. And what this is indicative of is this, look, for every 6 moles of H2O, you have 1 mole of C6H12O2, right? Now that we know this, sorry, let me go ahead and erase this correctly. Now that we know this conversion, we're able to plug in this. For every 6 moles of H2O, you have 1 mole of C6H12O6. Now this allows us to do the conversion, and what you should be plugging into your calculator essentially is just 5 divided by 6, because this 1 essentially gets ignored, right? It's just a 1 over 6. And your final answer when you plug this into your calculator should be 0.8 moles. And then your unit should be moles, obviously. And then that is of C6H12O6. And this is how you solve this problem. This was a relatively simple one, but this is how you solve this problem. Let's go ahead and take a look at problem number 2 now. Cellular respiration is a process that takes place in cells of organisms, including plants, to convert glucose into water and carbon dioxide. So once again, we're looking at the same chemical reaction, right? The photosynthesis or cellular respiration, which is just the reverse, right? Now the question is, if 165 grams of glucose is used during cellular respiration, how many moles of carbon dioxide will be produced by the organism? So I just want to write down here, before we get started, what we're being asked to convert from and what we're being asked to convert to. So we're being asked to convert from, right? We're given 165 grams of glucose. So that has to be what we're converting from. Grams of C6H12O6, right? And we are converting to, sorry, let me write that just a little bit neater. Grams of C6H12O6, and we are converting to moles of CO2, right? Because they are asking us for the number of moles of carbon dioxide produced by the organism. Now, this is the conversion that we're being asked to do. Now, are we doing a substance conversion? Indeed, we are doing a substance conversion. We are converting essentially from glucose to carbon dioxide. Now, what is our starting unit for glucose? Our starting unit for glucose is, we have 165, right? And that is in grams. So our starting unit is for glucose is 165 grams of C6H12O6. Now, what this tells me is that we are going to essentially have to go through moles here. We're going to have to convert from grams of glucose to moles of glucose, and then from moles of glucose to moles of CO2, right? Because we cannot convert directly from grams of one substance to the moles of another substance. Whenever you want to do a substance conversion, remember, and always keep this in mind, when you're doing your substance conversion, you have to go through that mole unit, right? And so let's take a look at how this looks when you're doing this, right? So we're going from grams C6H12O6, right? Now we're going from grams of C6H12O6, and we're trying to go to moles of CO2. So we have to go from grams of glucose to now moles of glucose first. Now for every, how many grams do I get 1 mole of glucose? This is where you use your molar mass of glucose, and the molar mass of glucose is 180.156. So for every 180.156 grams of glucose, I essentially have 1 mole of glucose. Now that we have moles of glucose, we're allowed to do that simple mole to mole conversion. Now, in order for you to do that mole to mole conversion, once again, as in the previous problem, we are required to balance this chemical equation up here. And when you balance your chemical equation, you should be getting a coefficient of 6 in front of oxygen, a coefficient of 6 in front of carbon dioxide, and finally a coefficient of 6 in front of H2O or water. And this now allows us to do a conversion from moles of C6H12O6 to moles of CO2, right? Because for every 1 mole, right, of glucose, for every 1 mole of glucose, we essentially have how many moles of CO2? We have 6 moles of CO2. Now that we know this, let's go ahead and take a look here, right? Now our starting unit, what's our starting unit? We started with grams of glucose, which is what we started with here. And what did we finish with? Moles of CO2. That is essentially what we were planning on doing from the beginning. So we know that our problem setup is now correct. And now really just plug this into your calculator and see what you get. And when you plug this into your calculator, what I would personally do is just go ahead and ignore all these ones here. What I usually do is just ignore the ones with the ones, and so I'll just do like 156 divided by 180.156, and then I'll multiply that by 6, and then once you do that, your final answer should actually be, taking significant figures into consideration, should be getting something around 5.495 moles of CO2. Let's go over problem 3 now. Sodium reacts with water to produce hydrogen gas and sodium hydroxide. Now we're given the reaction down here, right? Now the first thing we want to do now, knowing what we know from the previous problems, is just go ahead and balance this chemical reaction before we do anything else and get confused even further or tangled with the question. So once again, I'm not going to go over how to balance this. I'm just going to go over and go ahead and balance it. You should practice and pause the video and balance it on your own, but you should be getting a coefficient of 2 in front of sodium, a coefficient of 2 in front of the H2O, and a coefficient of 2 in front of the sodium hydroxide, right? And really just no coefficient in front of the hydrogen. Now let's go ahead and read the rest of the problem. If 30 liters of hydrogen gas was collected at standard temperature and pressure, how many grams of sodium were used? So this problem is way different from, not way different, but it's a little bit different from the other problems in that we have this new unit of liters introduced, right? And we're asked to convert from liters to grams of sodium, essentially, right? How many, so we're starting with liters of hydrogen gas because that's our initial given value. And they're asking us to convert to, once again, look at this, grams of sodium, right? Now I'm going to box this in because we know that we are going to be doing this conversion. Now this conversion involves several steps. One, because of the fact that we're converting from one substance, we're converting from hydrogen to sodium. And when you convert from one substance to the other substance, we are forced to go through, once again, moles. We're forced to go through moles. So we have to go from liters to moles of hydrogen. We have to go from liters of hydrogen to moles of hydrogen, then from moles of hydrogen to moles of sodium, and then from moles of sodium to moles of grams. To grams of sodium. Sorry about that. Now this seems very confusing, but just keep in mind for now that we have to go through the unit of moles. It's going to be way easier once I explain it as I set up the problem. So we're starting off with 30.0 liters of hydrogen gas, right? So we're essentially starting on the product side of this chemical reaction here. And they're asking us to convert to grams of sodium. Now the first step is going to be, as I just explained, to convert from liters of hydrogen. So we're going to be converting from liters of H2 to moles of H2, right? Because we have to go through moles, as I just said. Now, we know that for every 22.4 liters, you essentially have 1 mole. So for every one mole of hydrogen, you have 22.4 liters of hydrogen, right? Now this gives us a clean conversion from liters to moles. Now that we have moles of hydrogen, we can do a mole-to-mole conversion from moles of hydrogen to moles of sodium, right? Now, looking at this chemical reaction, for every 1 mole of hydrogen, we have 2 moles of sodium. We have 2 moles of sodium. Now that we know that, we are now at moles of sodium, right? So now we can convert from moles of sodium to grams of sodium, right? Which is just the next and really just the final step here. And it's not as difficult as it looks. It's really just the easy conversion. So from moles of sodium to grams of sodium. Now for every 1 mole of sodium, once again, this is where we use the molar mass of an element when we're going from moles of one element to grams of an element, or from grams to moles of an element. The molar mass of sodium is 22.99 grams. That essentially means that for every 1 mole of sodium, you have 22.99 grams of sodium. And so go ahead and plug this into your calculators. And the way that I would plug this into my calculator is I would do 30, ignore this 1, divided by 22.4, ignore this 1. Get your answer for that division problem. Go ahead and multiply that by 2. Once again, ignore this 1. Get your answer from that. And go ahead and multiply that by 22.99. And that should give you an answer, should give you the correct answer. You should get an answer around 61.6 grams of sodium. And so this is how we solve this problem. It's not too difficult. It's more complex than the last 2 problems that we went over, but it's totally doable. This is problem number 4. Let's go ahead and take a look at this one now. During combustion in a vehicle's engine, nitrogen and oxygen gas produce nitrogen monoxide. If 1.2 times 10 to the power of 24 molecules of nitrogen are used with excess oxygen, how many molecules of nitrogen monoxide will be produced? Now, the first thing that I want to do is go ahead and just balance this. And as I mentioned, I am not going to go over how to balance it. I'm just going to say that you need to put a coefficient of 2 in front of that nitrogen monoxide. Now, we can go ahead and get started, all right? So, our starting value is 1.2 times 10 to the power of 24 molecules of nitrogen. And they're essentially asking us how many molecules of nitrogen monoxide will be produced given that we start off with this many molecules of nitrogen. So they're asking us for molecules of nitrogen monoxide, right? So we'll be doing a conversion, and I want to write this down here, from molecules of nitrogen to molecules of nitrogen monoxide. This is essentially going to be a problem in which we convert from one substance to the other, right? Now, when you convert from one substance to the other, as I repeated in the previous videos, you have to go through the unit of moles. So let's go ahead and get started now that we know this. For every, or actually let's write our starting value first. 1.2 times 10 to the power of 24 molecules. Now for every 6.022 times 10 to the power of 23 molecules of nitrogen, right? You have how many moles of N2? You have 1 mole, right? So this is that clean conversion that's really significant in this problem. Doing that conversion from molecules, recognizing that you have to convert from molecules to moles, right? Recognizing that you have to go through moles is critical and really makes or breaks your success in completing these problems successfully. So now that you know that, you can convert from moles of N2 to moles of nitrogen monoxide, right? Because nitrogen monoxide is the substance that we are converting to. Now, according to our chemical reaction up here, for every 1 mole of N2, you have 2 moles of nitrogen monoxide. Now we can continue and do an easy conversion from moles of nitrogen monoxide to molecules of nitrogen monoxide. And once again, it's going to be the same thing. For every 6.022 times 10 to the power of 23 molecules of nitrogen monoxide, you essentially have 1 mole of nitrogen monoxide. And so this really allows us to go ahead and cancel these values out. Look, you can go ahead and cancel these values in your problem. And hence, when you calculate this problem in your calculator, all you're really doing is this here. You're just doing 1.2 times 10 to the power of 24. You can just ignore your 1 time, and so do this value times 2, right? Because that's our only remaining value now. And your answer should be around 2.4 times 10. Sorry, let me go ahead and write this problem down here, actually. I'm going to run out of space. So your answer should be 2.4 times 10 to the power of 24 molecules of nitrogen monoxide. So just go ahead and box this in. And this is how you solve this problem. It got a little scrappy and complicated in the end with all the crossings, but I hope you understood this problem. This is now the final problem for this video. Let's go ahead and get started. When marble statues are exposed to rain over time, the marble statue will begin to deteriorate. Marble statues are made of calcium carbonate, and rainwater is slightly acidic due to carbonic acid. We are provided with the chemical equation right here. Now the problem reads, if 1,254 grams of calcium sulfate, let's underline this right away, is produced from the decomposition of calcium carbonate and sulfuric acid, how many grams of calcium carbonate were decomposed? So we're asked for the number of grams of calcium carbonate that were decomposed, and they're giving us the number of grams initially, or our initial value is the number of grams of calcium sulfate. Now calcium sulfate in this chemical reaction is actually a product, and they are telling us how many grams of calcium carbonate decomposed, and calcium carbonate is a reactant. So what they are really giving us, or starting us off with, is the number of grams that were produced in this chemical reaction, and what we're really being asked for is the number of grams of calcium carbonate that reacted. So let me go ahead and just erase these scribbles. And so the first thing I want to do now is just go ahead and balance this reaction. And actually, it's already balanced. You don't even have to balance it. So now that we know this information, or given this information, we can go ahead and just write down here that we'll be converting from grams of calcium sulfate, right, to grams of carbonic acid, of calcium carbonate, sorry. So I'm going to box this in. Once again, we are doing a substance conversion. We're converting from calcium sulfate to calcium carbonate. Hence, we must go through moles. So we're going to have to convert from grams of calcium sulfate to moles of calcium sulfate, from moles of calcium sulfate. From moles of calcium sulfate to moles of calcium carbonate, and so on and so forth. This is how this problem setup should look like. We're starting off with 1,254 grams of calcium sulfate, right? Now, our first step in this process, since we know we have to go through moles. If you know you have to go through moles, right away you know that you're going to do a conversion from grams of calcium sulfate to moles of calcium sulfate. Shoot. Now, if you're going to do this conversion, you use the molar mass once again. For every 1 mole of calcium sulfate, we essentially have 136.14 grams of calcium sulfate, given that that is its molar mass. Now that you have the moles, now that we have moles of calcium sulfate, we can do a clean conversion from moles of calcium sulfate to moles of calcium carbonate, right? Because that's the substance that we are converting to carbonate. So we'll be going from moles of calcium sulfate to moles of calcium carbonate. And given that our chemical equation is already balanced, then everything is just at a 1-to-1 mole ratio. For every 1 mole of calcium sulfate, right, we have 1 mole of calcium carbonate. So that allows us to do that easy conversion there. Now that we have moles of calcium carbonate, we can go ahead and convert from moles of calcium carbonate. And remember, we're going all the way to grams of calcium carbonate. We're not stopping at moles of calcium carbonate. So we're going from moles of calcium carbonate to grams of calcium carbonate. For every 1 mole of calcium carbonate, you have 100.09 grams of calcium carbonate. That is its molar mass once again. And so we go ahead, we're done now actually with our problem setup, because as you can see, we started with grams of calcium sulfate, and we ended with grams of calcium carbonate, right? That is what we were going to do from the beginning. That was our goal, and that's what we did already. So now we go ahead and just, I'll put parentheses on here to make it more clear. And you can really just ignore this one here because it's just 1/1. It can be ignored. What I tend to do is always just ignore these ones, right? And so when I'm plugging this into my calculator, what I'll do is 1,254 divided by 136.14. Once you get that answer, go ahead and just multiply that by 100.09 grams. And that should give you an answer, I'll go ahead and write it down here, of 921.9 grams of calcium carbonate. This is our final answer for this problem. And this actually concludes this entire video. I hope that you grasped onto the idea of stoichiometry, which is really just going through moles, right? And being able to convert from one substance to the next, or from moles to grams or liters. It's not too complicated. I hope you understood this video. Have a great rest of your day. Thank you so much for listening.